All right, welcome to 6.1, day 2 of 3. So we are going to pick up where we left off last time. Last time, we finished up on this slide. We had a car taking a 90-degree turn in 6 seconds, and we determined the angular speed. Angular speed is angular displacement over time. Now here, we have a car. Why is the car able to take that turn? Well, we've talked about this in the previous video. The car is able to take the turn because of static friction. If there was no static friction between the tires and the pavement, the car wouldn't be able to make it around the turn. Okay, now, there are a couple of things that work here, and we'll talk more about this and, well, how does banking actually help the car take the turn? We'll get into that. Friction always points towards the center of the circle, always. Right, that's your centripetal force. Now, the last couple of points here on the slide, how does a plane follow a circular trajectory? We're not going to be covering that. So you can skip those last 2 bullet points and, well, the next slide as well. Okay, so I think you might have it in your notes. There are banking for airplanes. We're going to be skipping that. So that means you should end up, okay, 1 second. You should end up on this slide. Now, yes, we're on this slide. I want to talk a little bit about banking and how that helps. Okay, so if you've ever seen or heard of NASCAR racing, the cars essentially just keep driving in a circle or in an ellipse, but the road is not flat, it's banked. Even when you're entering the highway ramp is banked, it's not flat. When you're driving, it's banked a little bit, and the banking is towards the center of the circular path. All right, so why is there banking? Well, if you have no banking, this is the scenario you essentially have. You have your car trying to take a turn. Now let's look at the forces acting on it. Okay, so acting on this car, you have weight. You have normal force. And there is static friction pointing towards the center of the curve. Now, the way I've drawn these forces is the traditional way that I've done it in grade 11. I always draw the forces coming out of the center of the object. Now, if you took grade 11 physics this year with me, you didn't see this. You always saw friction drawn between the bottom of the tires and the pavement. Weight is always from the center of mass, and normal would have been from the bottom of the tires up. Okay, so sometimes we can always draw these forces from the center of the object as well. Although it is technically better form to draw it from where it's coming from, this is fine for our purposes right now. Okay, so this is what you have when there's no banking. The only force helping you make the turn is force of static friction, which is fine. But let's see what happens when you bank the road. Okay. If I bank the turn, so I have this banking angle theta, and I've got my car, and it's trying to take a turn. Okay, let's draw the forces acting on the car. Well, I've got weight, just like I did before. I've got my normal force, just like I did before. And now this is the tricky part, static friction. It depends how fast you're going, okay? If you're taking the turn very slow, okay? If you're going very slow, you're going to tend to fall down this ramp, and your static friction will actually point up the ramp, all right? If you're taking the turn very fast, okay, your tendency is to move off the road. Your static friction will point down. Now, there's an ideal speed at which you should take the turn, okay, and the ideal speed means you wouldn't actually need static friction to take the turn. But if you don't have static friction to take the turn, well, how do you take the turn? There has to be some kind of force pointing towards the center of the circular motion, and that's what you're going to see here. I'm going to take the normal force and I'm going to break it up into components. All right, so if I have my banking here and I define my directions x and y, x is parallel to the ground, y is perpendicular to the ground, which is the ground not being the ramp where the car is, the ground being here. I'm going to break up the normal force into its components. So I have nx and I have ny. It is the x component of the normal force that allows you to take the turn. And so when these banked highway ramps are designed, they're designed so that you don't actually need friction. So when you're told that there is an ideal speed, that is ideally if there's no friction. It's just the normal force that helps you take the turn. If there is static friction there as well, well, that just is there to help you, okay? So I just wanted to talk about that before we get into this next piece. All right, we talked a lot about angular speed, we talked about centripetal acceleration in part 1 of 3. So here we're gonna move into something a little bit in more depth. Okay, so we saw that the tangential speed is given by the product of radius, so the distance from the center to the object, and the angular speed. Now, if we square speed, we get r squared omega squared. Okay, well, where do you see the v squared? You see that in the formula for centripetal acceleration. Centripetal acceleration is v squared divided by r. And so that's what we're going to see on the slide. If v squared is r squared omega squared, well, you just stick that in the top. Now I've got an r squared in the top and I've got an r in the bottom. One can cancel from top and from bottom. Okay, so that leaves me with AC is equal to r omega squared. Now we have covered a lot of formulas so far in just 6.1 day 1 of 3 and now 6.1 day 2 of 3. Okay, so these are all the formulas that we have so far. Okay, now you haven't seen this one here yet, these FC formulas, the bottom two, but they can be easily derived using all the formulas that we've looked at so far. So you have 3 different ways of finding centripetal force, 3 different ways of finding centripetal acceleration, but the most important thing is you have to keep referring back to your data booklet, and that's what I keep saying. In your data booklet in 6.1, we're still in this box. There are not that many formulas in this box. So if the formula is not here, you have to know how to obtain it. Okay, so figuring out a lot of these formulas, well, we've done the derivations in these notes. Okay, some of them are not derived in the notes. For example, these bottom 2, but they're not a big step from centripetal acceleration. You just multiply this by mass. Okay, so that's a pretty easy step. I think you can do that. Okay, let's keep going. Angular velocity. Okay, so we talked about angular speed, right? You cover a certain angular displacement in a certain amount of time. If we put a direction with that, you've got angular velocity. That means we have to figure out how to give a direction. So even though we might have thought we were done with right-hand rule when we were studying magnetism, there's going to be another right-hand rule here. But it's far less complicated and there's only one of them. Okay, so this is how we're going to figure out the direction of the angular velocity. Take your right hand, okay? Using your right hand, your right fingers curl in the direction of the velocity. So right now my velocity is going counterclockwise. So the right fingers of my right hand, they have to curl counterclockwise. When they do that, my right thumb is pointing out of the board. That means the direction of my angular velocity is out of the board. Okay, and all of that is explained here on the slides as well. Okay, so you can always read through it at your leisure. Right fingers curl in the direction of the velocity. It's here, it's counterclockwise. Therefore, the direction of the angular velocity, which is omega, the fancy curly W, it's coming out of the board. Okay, let's keep going. Find the angular velocity in radians per second of the wheel on the shaft. It is rotating at 30.0 RPM. RPM is revolutions per minute, right? We talked about that in the last video. That gauge on your car that's telling you the RPMs of your engine. Okay, so 30 revolutions per minute. We already know how many times it's rotating per unit time. The problem is here, it's just not in the right units. When you convert units, you multiply by 1. That's all we're doing here. Okay, so we have 30 revolutions per minute. Okay, now I need to get rid of the minutes and make that into seconds. So seconds is going down on the bottom, minutes is going on top. 1 minute is 60 seconds. This way I cancel my minutes and I'm left with revolutions per second. Now I don't want revolutions per second, I want radians per second. So I need to change revolutions to radians. multiply by 1 again. I'm getting rid of revolutions, it's going in the bottom. And I want radians, that's going on top. Well, 1 revolution is 2 pi, or 360 degrees, okay? So we have another cancellation here. Revolution with revolution. So I'm left with radians per second. When you calculate this, you're going to get, let's actually just do it from scratch here. So 30 divided by 60, that's half, times 2 pi. Okay, so that's pi, 3.14, right? Here, I mean, you can give your answer as pi radians per second, but since we're given 3 sig figs there, we want to give 3 sig figs in our answer. Remember, for math, exact. For physics, you give it to the number of sig figs. Okay, so 3.14, this is radians per second. Now, based on this picture, if we want to figure out the direction of the angular velocity, you see the direction it's rotating, it's going into the board at the top and it's coming out at the bottom. So using your right hand, if I curl my fingers in the direction of that velocity, my thumb is pointing down the shaft, so down and left. So down and to the left of the shaft. And put your answer in a box. Okay, hopefully that's okay. Now on the next slide we're going to see some examples of centripetal force. Okay, so 5 examples of forces that are centripetal in nature. We actually saw quite a bit of these examples and I explained a lot of them in the last video. Okay, so you have, let's say you have a ball attached to a string and you're whirling it around your head. Well, what's the centripetal force there? It's tension. Okay, if you have a car going around a banked turn or a non-banked turn, okay, you either have static friction or a component of the normal force helping you take the turn. That's the centripetal force in those cases. Hey, if you have the Earth orbiting around the Sun, or the Moon orbiting around the Earth, or a satellite orbiting around the Earth, gravitational force is the centripetal force, okay? So there are many examples listed here, so let me put them up. A lot of them we talked about. Okay, so we've got gravitational force, friction force, tension force, electric force, right? We talked about this in the last video as well. Electric force usually is not a centripetal force, but it can be. For example, if you have the positive nucleus of the hydrogen atom, and you have the negative electron orbiting around the nucleus, well, it's moving in a circle, right? You might not know exactly where that circle is, but we know it's moving in a circle. That's centripetal force. Magnetic force. Well, magnetic force, absolutely. Okay. Moving on. Dobson is watching a 16-pound bowling ball being swung around at 50 meters per second by Arnold. If the string is cut at the instant the ball is next to the ice cream, what will the ball do? Will it A, follow the path A and strike Dobson's ice cream, B, fly outward along curved path B, or C, it will fly tangent to the original circular path along C? This is actually a very common multiple choice question in first year exams, and although the question itself is easy, a lot of people will make the mistake because maybe they're not making the connection here. When we investigate circular motion, we always say that there is a constant speed and that the speed or the velocity vector is always tangent to the circle, always. What that means is if you were to take a ball attached to a string and you whirl it around your head, if you cut the string at any point in time, that ball will continue moving in whatever tangential direction it was moving at that particular moment. Okay, so like I said, this scenario is often given, to first year students, and a lot of people will make this mistake. So let me show you another example. This is usually the scenario they give. You have the sun, and you have the Earth orbiting the sun. Now, for some reason, as the Earth orbits the sun, the gravitational field is turned off, okay, from the sun. And so then, where does the Earth go? So if the gravitational field from the sun is turned off here, and the Earth is orbiting counterclockwise in this fashion, well, where is the Earth going to go? It's going to move in that tangential direction it was moving at that point in time. And we know that the velocity, like I keep saying, is tangent to the circle. So if you turn off the gravity at this point, the Earth would just keep moving in this direction. It wouldn't keep moving in a circle. Whatever direction it's in at that point, Newton's first law says it's going to keep moving in that direction. Okay, so that tells us that the answer here has to be C. Okay, it's going to move tangent to the circle. All right. Example, suppose a 0.500 kilogram baseball is placed in a circular orbit around the Earth at slightly higher than the tallest point, Mount Everest, which is at 8850 meters. Given that the Earth has a radius of 6.4 times 10 to the 6, so 6,400,000 meters, find the speed of the ball. All right. So we have an object in circular orbit. As soon as you see that an object is moving in a circle, think centripetal force, think net force. And then what is the centripetal force? Okay, so in the last unit, we would see that the centripetal force was the magnetic force. And then we would set mv squared over r equal to qvb sine theta. And we would come up with an expression for the radius of the circular path or the speed. Various things could be determined. So, all right, so we have the mass of this baseball, it's 0.500 kilograms. It's placed in a circular orbit around the Earth that's slightly higher than the tallest point. Draw a picture. Okay, so you've got the ball at this height, so that means the distance from the Earth's center is not only the Earth's radius, but also this extra height, that extra distance, which is 8850 meters. So r, that distance from the center, is radius of the Earth plus 8850, and you're given the radius of the Earth. Okay, so this thing is orbiting around the Earth because of gravity. So therefore, I'm going to set the centripetal force equal to the force of gravity. Now those of you that took grade 11 physics with me this year, that might look a little strange to you. Fg, that's force of gravity. You always saw it as weight. And that's fine. If you want to set Fc equal to W, that's fine. It's the same thing. Okay, weight is the same as force of gravity. Now, for an object experiencing the Earth's gravitational field, W or Fg is equal to mg. And centripetal force, you can look that up in your data booklets, mv squared over r. Now we're looking for speed here. Notice that mass cancels on both sides, so I don't actually need the mass. Rearranging for v, I have g times r and square root that. Now, this is a little bit of an assumption that's not exactly correct here, but we're going to make it because there's no other way for us to answer it. G, we're going to plug in as 9.8. Now, you know, if you're that high off the surface, it's not exactly 9.8, it's probably fluctuated a bit. This is a fine value to use, but just keep that in mind. As you move away from the Earth, if you're significantly far, so if we're dealing with a satellite, G is less than 9.8, significantly less than 9.8. Not that it would become 5 meters per second squared necessarily, but it's enough for us to write down a different value. All right, so G is 9.8. The radius of the path, it's the radius of the Earth plus 8850. So that's going to be 6, so that's 6,400,000 plus 8850. So 6408850. Let me just make sure that's okay. Yeah, so that's 6,400,000 plus 8850. So I just stuck them in right away. Okay, so let's calculate that. So 9.8 times 6408850 divided, square root 7925. 7925 meters per second. Now, looking at the values in the question, I know the height of Mount Everest is 8850. That's 3 sig figs right there. But unfortunately, the radius of the Earth has only given us 2 sig figs. Now, the mass, that's 3 sig figs. The zeros that trail the 5 count. Okay, so that means when I'm working with all these numbers, I have to work to the least number of sig figs, so that's 2 from the radius of the Earth. So rounding this to 2 sig figs, that's going to be 7,900 meters per second. Okay. Now in the notes, it's rounded to 8,000 meters per second, so just go with it for now. Okay, this would be correct according to sig figs, but we're going to use that nice number of 8,000 later on when we do a calculation. Okay. So using the same scenario, how long will it take the ball to return to Everest? So now we're trying to figure out how long it takes to go from here around once and end up back where it started. So the time it takes for an object to move around a circle once is called the period. So we're looking for capital T. We already know the speed, can't figure out the time, right? So, well, that's what we're looking for. Right, so time, speed, what's the relationship there? It's distance. So distance is equal to speed, let's see, actually, hang on. Distance is equal to speed times time. Meters per second times seconds will be meters. So if we're rearranging for t, that would be s divided by v. All right, now when you're moving in a circular path, the distance that you travel is the circumference of a circle. Excuse me. So that's 2 pi r. R being this value right here, right? So that's 6.408850 times 10 to the 6. That's the distance from the center of the Earth to the surface plus that extra 8850. Okay, so 6,408,850 divided by v, which is 7,900. Although, like I said, in the slides, the number 8,000 is used for calculations, which is fine. Okay, so we have 2 pi times 6,408,850 divided by 7,900, and we're left with 5097.2. Keep in mind that units are coming out in SI units. Because you calculated this in seconds, right, it's going to come out as a big number. Now, you don't want to leave your answer like that. It looks a little bit rough. If you want, you can leave the answer in seconds, but you can always convert it to minutes. You can convert it to hours. Okay, so to convert it to minutes, divide by 60. To convert it to hours, divide by 60 again. We'll leave it like that for now. Okay. Let's keep going. This next scenario is interesting, actually. Explain how an object can remain in orbit yet always be falling. So to understand this, we have to understand this idea of something called Newton's canon. Newton's canon is a hypothetical experiment, also known as a thought experiment, where we analyze what's happening with an object due to the laws of physics that we know. So again, this is called Newton's canon. The idea is Newton is standing on one part of the Earth and he has a cannon and he's going to shoot cannonballs out of it. And those cannonballs will have different speeds and different curvatures, and we're going to analyze what's going to happen. Now, this is obviously an exaggerated picture. I might just go with this for a moment. Okay, so you've got this cannon. It's shooting cannonballs out. Now, assume the first cannonball is ejected with a certain speed. Not too fast, not too slow, but what's going to happen? It's going to travel straight, and then gravity pulls it back down, and it hits the ground a certain distance later, right? Now, if you want that cannonball to travel faster, you eject it faster, right? So if you want it to actually travel further, you will eject it faster. So if you eject it faster, it will cover a bigger distance, but again, gravity will pull it down and it will smash into the Earth. Now, let's say you project it at this ideal velocity. Okay, so fast that it'll surpass this speed, but not that fast that it would escape Earth's orbit. If you project it at a certain particular speed, this thing is just going to keep falling and falling and falling, but it never falls down. So it keeps trying to fall towards the Earth, but the Earth's surface curves away from it at the exact same rate. And so it never falls down, but it's always falling. And so this tells us that when an object is in orbit, that means it's always falling towards the Earth. So if you're ever asked, is the moon falling towards the Earth? The answer is yes. The moon is always falling towards the Earth. It just never falls down because the curvature of the Earth always bends away from it at the right rate. Okay? So that's Newton's cannonball. You eject something at the right velocity and it will travel far enough that it just keeps falling around the Earth. That's what's on the slide. So I'll leave the notes up here if you want to take a moment, freeze the video, pause it, and copy it down. Okay, moving on. Find the angular speed of the minute hand of a clock and the rotation of the Earth in 1 day. Okay. Two different things here, I know. There's a reason. We're going to compare these values. Angular speed of the minute hand. Okay, so we haven't talked about angular speed for a bit. That's omega. Omega is theta over t, angular displacement per unit time. Now, the minute hand of a clock, we'll just assume that it's going around once. So that means the angle it's moving through is 2 pi radians. Now, the minute hand, how long does the minute hand take to go around the clock once? It takes 60 minutes, right? So 60 minutes goes on the bottom. Now, I need to have the value for omega in radians per second, not radians per minute. So I got to convert that minutes to seconds. So I'm going to multiply by 1 down here. So getting rid of minutes, putting seconds, 1 minute, 60 seconds. So 60 times 60 is 3,600. That's how many seconds I have. Okay, so 2 pi radians divided by 3,600 seconds. So we just have to calculate what that's equal to. So 2 pi divided by 3,600, that's 1.7, that would be 1.75 times 10 to the negative 3 radians per second. Again, it's a reasonable number of sig figs here because we're not given the data directly in the question. So there's omega. No direction needed, right? It's angular speed. Okay, and find the angular speed of the rotation of the Earth in 1 day. So again, omega is theta over t. Now, when the Earth is rotating, any point on the Earth in 1 day, in 24 hours, well, it goes through 360 degrees, or 2 pi radians. So we still have 2 pi radians, and like I just said, we know that takes 24 hours. Okay, so we have to convert hours to seconds. We already know that 60 minutes, or 1 hour, is 3,600 seconds. So 24 hours, that's going to be a simple conversion. 1 hour, actually let's stick the 1 in the middle here. 1 hour is 3,600 seconds. So hours cancels with hours. 24 times 3,600, that's how many seconds you have. And divide 2 pi by that number. Okay, so when you do that, let's see here. Yeah, it's a very small number. 0.0000727. 1, 2, 3, 4 zeros. Yep. Radians per second. So this is the angular speed of the Earth. And this is why you don't feel the Earth rotating, because it's so small. Every second going through that many radians, that's almost nothing. This is why we don't feel it. Okay. The next topic, the Foucault pendulum. This is a really interesting idea. Let me grab one. right, I've got my ball attached to a string. I'm gonna grab one more thing. The globe. All right, so I'm gonna set this down here, and I've got a pendulum. Now, a pendulum is an object of mass attached to a string that undergoes simple harmonic motion. So like this. Right, so this thing is oscillating back and forth about some equilibrium point, which is in the middle. Right? Now, in reality, the amplitude of these oscillations keeps decreasing due to air resistance, but we don't look at that, right? We're not looking at that right now. Assume minimal energy loss. Now, if I was to have a very nice pendulum, okay, so this thing, imagine it wouldn't lose energy, or it lost so little that it was negligible. This thing is swinging back and forth. If I left this thing here overnight for 24 hours or 48 hours or a week, if it doesn't lose energy, and if I came back in the room a week later, it would still be moving like this, right? Back and forth to that side of the wall and back to that side of the wall. Now, you might say, well, okay, that's interesting. Should it actually stay like that? Well, the answer is no. The only reason if you come back exactly a week later or 24 or 48 hours later that it would be moving in the same orientation is, well, you didn't come any time in between. If I came 6 hours later, so let's say I set this thing in motion, it's moving like this. If I come 6 hours later, this pendulum is not going to be oscillating back and forth like this, okay? It would actually be moving something like this. Now that might seem very, very strange to you, okay? And after another 6 hours, it's gonna be like this. And then after another 6 hours, it's gonna be like this. And then when we're back to 24 hours, it's gonna be like this. Okay? Now, why is that the case? Why is this rotating? When we're standing here on the Earth right now, the Earth seems stationary to us, like it's not rotating. This thing is in motion, okay? So when we look at things in physics, we look at an object's motion relative to something else. Relative to what we see right now, the Earth appears stationary, this thing is moving, but it's rotating. So to understand why it's rotating, put yourself from the frame of reference of the pendulum instead, not from the Earth where you're stationary. Okay, so now we're gonna pretend we're right here on top of northern Canada. And this thing is oscillating back and forth like this. Now from the point of view of the pendulum is going to keep swinging back and forth. But if I move the Earth from underneath it, if it rotates, right? As it rotates, technically this pendulum is facing a different direction every time. Okay, so now I've rotated the globe, well, half a revolution. Now it's rotating above Russia. Okay, now that's not the case that it's actually going to be rotating above Russia. The idea is it's changing its angle, right? So now I'm almost there, 270 degrees I've rotated the globe. Okay, so that is from the perspective of the pendulum. The pendulum looks like it's just going back and forth, but the Earth has rotated underneath it. Once I get to 360 degrees, well, how long does it take for the Earth to go through 360 degrees? 24 hours. And the pendulum is back in its original orientation. But the idea is, if you're in the frame of reference of the pendulum, the Earth is moving. If you're in the frame of reference of the Earth, which we are, you would see the pendulum change direction. So this thing, over time, would just keep rotating. And in one day, it would make a full 360-degree revolution. Okay, so on this slide, it says, well, explain how it can be used to tell time. Well, if this thing makes one full revolution, that's 24 hours. If it makes a quarter of a revolution, that's a quarter of 24 hours. That's 6 hours. You come back after 48 hours, that's 2 full days. It's going to look exactly as you left it. You come back after a week, it'll look exactly as you left it. Okay? That's how you can tell time. Now, what I wanted you to know is how to use it to tell time. I will not ask you to calculate time that has elapsed due to a Foucault pendulum. Okay, so what that means is I'm going to go ahead and just skip through this piece right here Again, just make sure you understand it conceptually, what I've just demonstrated. But as for the calculations, and the calculations appear on the next slide, this one here. If you want, you can follow it at your own leisure, but I'm not going to be going through it, nor will I test you on something like this. We're going to go to this next piece right here. Okay, find the apparent weight of someone standing on an equatorial scale if his weight is 882 newtons at the North Pole. An equatorial scale is just a scale at the equator. Now in grade 11, we looked at the motion of people in an elevator. And when you have a person in an elevator and they are standing on a scale, well, there's two forces acting on the person, even if they're not standing on a scale. There's two forces. There's the normal force, right? The floor of the elevator is pushing up on the person, and there's the weight, the force of gravity that pushes down. Right now, when you have a scale, scales read the normal force, right? Your weight is on the scale has to push back upon you with the same force. So whatever force the scale has to push back upon you, that's what it shows. Okay, so what's the point of that? Well, we saw that if you're in an elevator and the elevator is at rest, it starts to move, right? So if you enter the elevator on the ground floor, on the lobby, you press 6 and the elevator starts to go up. Well, before it reaches the constant velocity, you have to get to that velocity. If you're starting at 0 and you're going to V, you have to accelerate. Okay, and when you accelerate, there's a net force. That means your two forces, Fn and Fg, are no longer balanced. Okay, now Fn is much bigger. Since you're accelerating up, your upward force is bigger, hence your scale would have a much bigger reading on it. Okay, and then the opposite is true is if you go down. So when we say find apparent weight, that's the normal force. Okay? And anyway, scales do read your normal force. Now, the first thing, recall that omega equals that really small number in radians per second anywhere on the Earth. We just found that in an earlier example. And we said that's why you don't feel the Earth rotating, because the angular speed is so small. But that's true for any point on the Earth. Any point on the Earth goes through the same angle in the same time. It doesn't move through the same distance in the same time, which is why its speed v is different. But the angular speed is the same. Okay? Now, the blue arcs that are being drawn, I don't know how well this is showing up on the video, but there are 3 blue arcs, one at the equator, one near the North Pole, and one kind of halfway in between. Those are lines of latitude. And if you study geography, you know what latitude and longitude are. Right? So we've got the 0-degree line of latitude at the equator, 90 degrees all the way on top at the point, okay? And something in between, you have different lines of latitude. So, now this for sure, I'm sure you have trouble seeing, there is a white line that is drawn from the center of the Earth to the edge of the Earth. That's called the radius, right? So you know that. That's the radius of a sphere. Now, what we're going to try to come up with here is an expression for the distance of the Earth, at the point of the Earth that you're at, to that central rotation axis. Okay, and that is what we're going to call r. So this is in yellow. I'm sure you have trouble seeing this. Lowercase r is the distance from the axis of rotation that you're rotating. That's what you care about. When something's rotating, you care about where the axis of rotation is and how far you are from that rotation axis. That's lowercase r. And using lowercase r, to find that, using a capital